Yeah, there. So today we are going to solve another LeetCode problem named unique paths. Medium level, and it goes like this. There is a robot on an MXN grid. The robot is initially located at the top left corner. The robot tries to move to the bottom right corner. The robot can only move either down or right at any point of time. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. The test case generated so that the answer will be less than or equal to 2 multiplied by 10 in the power of 9. So there are some examples here and constraints showing that both m and n greater or equal to 1 and less or equal to 100. All right, so let's put our robot on some huge abstract grid of m rows and n columns. So we are putting it to the top left corner. From this corner, it could move either one step to the right or one step to the bottom. In either way, the new position would create a set or a tree of unique paths to reach the finish point. So we could calculate these unique paths for a position one step to the right, for a position one step to the bottom, then make a sum and return it as a result. So what are these numbers? How many unique paths are there for a position one step to the right? Basically, we need to calculate the unique paths for another grid with the same amount of rows, but the amount of columns would be subtracted by 1. As for the position when we are moving the robot one step to the bottom, well, we need to calculate the unique paths for another grid, which would have the same amount of columns, but one less row. So, as you see, we have some kind of recursion here, and let's write it down. So we are going to return the sum of two unique paths of m minus 1 rows and n columns grid, and also the grid of m rows and n minus 1 columns. Nice. So when are we going to stop this recursion? So if our robot reach the right edge of our original grid, then it is not able to move in any other way than just move straight forward to the finish point. So it has only one unique path. The same we could say when the robot reaches the bottom edge. From this bottom edge, no matter what position the robot is there, it has only one unique path to go straight forward to the finish point directly to the right. So we could calculate these unique edge cases. For these edge cases, as you can understand, either the grid's amount of columns would be 1, so it would be a grid of 1 column, or it could be a grid of 1 row. So let's check it first, that we are going to do our calculations only if the amount of rows is not equal to 1 and amount of columns is not equal to 1. Otherwise, there is only one unique path for such grids. And that's it. Let's check how it works. Nice. As you see, there are no compilation issues and the code is really simple. However, this code could be even better. imagine there is some abstract point on our grid somewhere in the middle, and our robot is able to reach this point in absolutely multiple amount of ways. What is interesting is that, well, we are able to calculate the unique paths for this point, and the unique paths for this point is going to be the same number, no matter in what way our robot have reached it. So we could calculate it only once when the robot reaches it first time, and use this number later whenever robot reaches it next times. So as you understand, we are going to have some kind of cache which is going to store our results. And the cache needs some kind of keys, so it's going to be a dictionary. And well, we are going to use our m and n couple of values for that. Unfortunately, we are not able to use this with tuples because they are not hashable. So let's create our own type, struct size, which is going to be hashable. And it's going to contain two values, m and n. Nice. So we are going to use this type as a key in our cache. And now we are able to, well, first calculate or construct this structure for our couple of values and check if we have a result in our cache for this size. If there is, then we could return the result straightforward. Otherwise, we need to, well, calculate the result first, then put it to our cache, and then return it at the end. Let's check for any compilation issues. Oh yeah, the cache should be the variable, of course. Nice. And now let's submit the solution. Great. So as you see, the execution time of this solution on all the test cases stays somewhere on the edge of the threshold, and that's why it shows that it was executed in 0 milliseconds and it beats 100% of other submissions. And that's it for today. If you'd like to see me solving other LeetCode problems, then put your request to the comment section. See you next time. Cheers.